Hello and welcome to Aerospace and Mechanical Lab 2. Today we are going to discuss the theory of Lab 1 structural dynamics. Lab 1 is going to have two different parts. The first part we are going to focus on buckling, failure of structures specifically. Today we are going to review the buckling theory and discuss the lab itself. For the second part of the lab, we are going to discuss the vibration theory, then move on to the theory of free beam vibration, cantilever vibration, and as part B of the second part of the lab, we are going to discuss the damping and damping ratio calculations. Okay, so in your courses so far, you have seen different types of failures. The failures themselves can happen because of different reasons based on the type of structures, conditions of support, kinds of loads, and the material that is used. And we also we always want to design our material, design our structures in a way that the displacement remains within the tolerable limits. And of course, the strength and the stiffness of the material are always important in the structural integrity of the material. Today, we are going to be focusing on buckling. In buckling failure, the conditions of support become much more important and much more prominent compared to other types of failures. Not that it is not important in other types of failures, but today we are going to focus on the conditions of support specifically. So, in order to understand buckling or the Euler's theory for buckling, which is the buckling of columns specifically, we have to define a column first. We define a column as a beam that's length is an order of magnitude larger than either of its other dimensions. This specific type of beam is called a column. And buckling itself happens when a column undergoes compressive loads and it experiences a lateral deflection, the deflection in this direction. That deflection is called buckling. The important part of the buckling for us, though, is the critical load of buckling. So the idea is if your load is smaller than the critical load of buckling, even if the deflection happens, your column is going to be stable, meaning that it will go back to its original location when the load is removed. If your load is equal to the critical load of buckling, we are going to see a neutral equilibrium, meaning that the column will remain at its deflected or undeflected position. And when the load is larger than the critical load of buckling, the column becomes unstable, meaning that it keeps deflecting until it breaks. You have to keep in mind, though, that the critical load of buckling is usually smaller than the yield load. So before any plastic deformation happens, the buckling will happen. Okay, so all of this tells us that we have to focus on calculating the critical load of buckling to avoid any failures, right? And we're going to use the Euler's buckling method, which was one of the first methods developed to calculate the load of buckling. To use these methods, a couple of conditions need to be met. The column needs to be perfectly straight. The materials we use in the column needs to be homogeneous and behave in a linear, elastic manner. And the load that is applied needs to be applied to the centroid of the cross-section. And it also needs to buckle or bend in a single plane. The reason we have all of these is because essentially Euler assumed all of these when he developed his model. Otherwise, he couldn't have integrated the equations to find the final equation for critical load of buckling. Of course, as we said in the beginning, these critical load values depend heavily on the column supports. in order to bring in the supports, the importance of or the influence of supports in our equation, we are going to bring a correction factor in the equation that we're going to talk about later. And as you increase the load, you have to keep in mind the shape of buckling might change. These shape changes are called modes of buckling. Right? That is not an important part of the discussion for us, but the idea simply is first mode of buckling, your column is going to buckle like this. Second mode of buckling is going to buckle like this. And the third mode of buckling, you are going to see a wavier pattern and so on and so forth. But again, we are going to focus on the first mode of buckling. Our critical load is going to be essentially in the first mode of buckling. How do we calculate the critical load? This is the equation we use. Of course, it has a mode factor for all of our calculation. This mode factor n is 1, so this doesn't really show up in your calculations. We have a pi squared, that is the number pi, 3.14. We have the Young's modulus, which would be your goal. In the lab, you're calculating the Young's modulus for the columns. The moment of inertia for that specific column. And this value K is the support correction factor. So depending on the support, this value is going to differ. Euler himself developed this formula for a pin-pin support, which essentially means the correction factor for a pin-pin support is going to be equal to 1. And the other correction factors are going to be determined according to how similar is the buckling pattern to the pin-pin buckling. And L is going to be the column length. Okay, these are the K factors. So pinned end, again, this is the shape of buckling. Your factor is 1. If you have one free and one fixed end, you're essentially seeing half of a pin-pin buckling, meaning that your correction factor is going to be 2. Fixed end, you are going to see a smaller buckling. Essentially, this is similar. Half of the beam buckles similarly to the pin-pin. Correction factor is 0.5. Same idea for pinned and fixed end. These are the 4 different scenarios that you are going to see in the lab, and these will be the correction factors you need to use in your calculations. Okay. I have a video in which we talk about the buckling. I'm not going to play this video in the recording, but I will upload a PowerPoint so you can go back and watch this video. But this is an interesting video. Maybe I can play a couple of. So it gives us a very good idea of where all of these factors come from and what do they mean. You are going to benefit from watching this video, so it's not a bad idea to watch it. So the first part of the lab, buckling of columns, we have essentially different supports. You have a fixed free bar, that is your first one. You have a pin bar, you have a fixed pin bar, you have a fixed bar, and for all of these, you are going to measure the loads, which means that you're going to have 4 critical loads, 4 modulus of elasticities. And if you do the experiment a couple of different times, even more moduli of elasticity, meaning that it is going to be easy for you to do confidence interval calculations. Okay, and this is the buckling shape we expect. As soon as you see these shapes, your column has buckled. Okay. The goal here would be to measure the critical load by adding weights to your system, and we want to use the correct equation, of course, based on the support you have. You have to calculate the moment of inertia, and eventually you find the modulus of elasticity of the column that needs to be presented correctly. So you have to do a statistical analysis and present the confidence interval. The second part of the lab that has itself has part A and part B, is focused on vibration. First, we need to define vibration. First, vibration is a mechanical phenomenon where oscillations occur. We have two different types of vibrations: free vibration, and when you have an initial input and your system is allowed to vibrate freely; forced vibration, where you have a time varying disturbance, is applied to a mechanical system. Yeah, we can have different types of input: periodic, steady state, transient, or a random input. And we can also have a damped vibration, where the energy of vibration starts dissipating by friction and other mechanisms, meaning that the vibration is going to die down. So the second part of the lab will focus on calculating the damping ratio. Okay. Vibration is usually modeled as a spring mass damper system. So you have a mass, you have a spring, you have a damper, right? And for a spring mass damper system, we are going to have, can write this specific type of equation of motion. This is your mass, damper, and a spring. Okay. We don't really have a closed form solution for this problem if you do not have the appropriate boundary conditions. Mode shapes in general are going to look like this, and we do have a natural frequency that we can calculate for any vibrating systems. In this lab, we are interested in the mode shapes, essentially how the vibration happens, and we are also interested in these points. As you can see, this is going to be your amplitude, essentially how high your beam is vibrating. But as you can see, sometimes, this is a graph with respect to time, but we can do a y with respect to x, which we're going to see in the next, let's actually look at it here. So this is your length, x is divided by 8. This is going to be the amplitude of vibration. This would be your mode shape depending on the natural frequency, right? This is the maximum vibration you can see in the normal direction, and this is the location on the beam that you are standing on. We are interested in these. And you definitely need to do the experiment a couple of different times, but we're going to get to that later on. Okay, let's go back to the original equation. This is your original equation. We used to ask the students to do a lot of calculations here, not anymore. We just provide you with the numbers. We just do the final calculations and the experiment itself. Okay, so we will give you a beam like this that is 1 meter long, 12 millimeters deep, and 3 millimeters high. So essentially a very long beam, right? The idea is this beam is connected to a shaker in the middle and is going to shake the beam. You are going to record the locations where the lateral displacement is 0. These are called the nodes, right? That is what you will be measuring in the lab, the location of these nodes where the lateral vibration is 0, right? And we are going to see what theory fits this experiment best. That is the goal of the lab. Shaker in the middle, 2 free ends. So as you can guess, this is not a free beam because there is a shaker in the middle, right? But we are going to see, you're going to investigate whether a free beam theory actually can predict the correct node locations. Okay, I have a video here as well. Let me actually, you should definitely go and watch it. You can see these are the node locations where the sand moves to. There are essentially 0 displacements, and you have your free beam. Please go ahead and watch this video at your own convenience. This will be uploaded. I've given you our specific beams modulus of elasticity and density, and these need to be measured by you in the lab. Right? The beams should be 1 meter, around 1 meter, might be 95 centimeter to 1.05 meters. So, and we are using aluminum beams, so not steel beams. in the lab. Okay, so with a free beam perspective, the idea of a free beam is for the first natural frequency, the mode shape is going to be like this. That is the theory of free beam, right? Meaning that there will be two locations where the lateral displacement is zero. The first the first natural frequency for the free beam theory is given to you. All of this will be populated in the lab memo and also at the end of the lecture notes. So no difficult calculations in this lab. All of the numbers you need will be provided to you. And in general, the idea of vibration modes is if you go to the second natural frequency in a free beam, your mode shape is going to change, and you are going to find three locations where the lateral displacement is zero. Third mode of vibration free beam, we're going to see four locations where the lateral displacement is zero. So you essentially set your signal generator to the natural frequencies of the free beam theory, find the location of these nodes, compare those locations to the theoretical values that are given to you in the lab memo, and find the error, essentially. That would be the first step. The second step would be, and we have this huge equation. This is the lateral displacement, normal displacement as a function of the location on the beam. Again, you don't need to do the calculation using this equation. This is just a general equation, but we will give you the locations at which this normal displacement is zero, node location specific. So we have compared our real scenario, the shaker with the two free ends, to the free beam vibration. And we know what the error is. The next step is to apply a different theory. So this shaker, this beam, can be divided in theory to two cantilever beams. The shaker in the middle can act as the fixed end. Again, this is not fixed, this is vibrating. So that is where the theory differs from the real experiment that you're doing. This is vibrating, this is moving in the middle, right? And has a free end. So we are dividing our beam to two cantilever beams. This is a theoretical perspective that we are applying to a real world problem. Same idea apply here. For different natural frequencies, we are going to see different mode shapes and different number of nodes. The difference would be for the first mode, there is zero nodes in the cantilever beam. Second mode, which happens at the second natural frequency, there will be one node. You find the location for this one compared to theory. In the third mode, there will be two. Again, find the location compared to the theory. This is the equation, but you don't need to use this equation. We will give you the values you need. Okay. And then when you're done, you essentially, whichever theory gives you the less error, whichever theories node locations is closer to the actual node location you have measured in the lab, is going to be the theoretical framework you can use to analyze the shaker with two free ends. And that will conclude the first part of the lab. The second part of this vibration lab is going to focus on damping. Right? The idea here is that you don't really have an vibrating input anymore. The energy of vibration is going to dissipate, meaning that it will stop vibrating. And your mode shape is going to look like this. Your vibration shape is going to look like this. You can see you start with a high degree of vibration, it will go down to closer to zero. You will be given a strain gauge that is already pre-installed on the beam, and that those strain gauges connected to a DAQ and a National Instrument device is going to help you find this graph, right? And I have actually talked in detail about how to create a LabVIEW code to help you find this graph. You make sure you need to follow that recording, lab recording, as closely as possible, and create a good code that will help you have this graph. When you have this graph, again, this is a dying vibration, and you are going to take the first or second order, it doesn't really matter which one you take. You will take the first amplitude and the last one, or first amplitude or the 50th one, doesn't really matter. You should know the amplitude. You should put in here. This is the displacement, the lateral displacement amplitude of your 0th cycle or the nth cycle. And this is the number of cycles. Using this, you can find the logarithmic decrement. And using the logarithmic decrement, you can find the damping ratio epsilon by dividing it by 2 pi. So what you need from this is to make sure you follow the LabVIEW guideline that I am going to post. Make sure you have this graph. Take any two locations, find their amplitudes, count the number of cycles in between them, do the calculation. And you have the damping ratio. All of the, sorry, this is lamp 1. Let me actually delete this. But all of the natural frequencies you need for the free beam theory and the cantilever theory is given to you. And again, the idea would be for you, for the first part, to use the first 3 natural frequency, natural resonance, and their corresponding node positions, compare it to the real measurements that you have in the lab. Part 2 is going to focus on writing the LabVIEW code. The idea would here for you is to learn how to write a LabVIEW code as well, and then find the damping ratio of the beam. Thank you for listening. Please let us know if you have a question or concern.